Imagine harnessing the very power that fuels the stars. That's what humanity did in the 20th century. We unlocked the secrets hidden deep inside the atom, the fundamental building block of everything we see and touch. This discovery gave us two distinct ways to release an almost unimaginable amount of energy from a tiny amount of matter. These two methods, known as nuclear fission and nuclear fusion, are the engines behind the most destructive weapons ever created by humankind. They represent a monumental leap in our scientific understanding, but also a profound challenge to our collective wisdom and survival. One path involves splitting atoms apart, the other involves forcing them together. Both lead to an explosive force that can reshape landscapes and alter the course of history in a flash. The first type of weapon, the atomic bomb, relies on a process called fission. Think of it as a cosmic game of billiards at the subatomic level. You take a very large, unstable atom like an isotope of uranium or plutonium, and you shoot a tiny particle called a neutron at it. This collision is so energetic that it causes the large atom's nucleus to split into smaller pieces. This act of splitting releases a tremendous burst of energy, along with more neutrons. These newly freed neutrons then fly off and strike other large atoms, creating a self-sustaining chain reaction. It's a cascade of atomic demolition, growing exponentially in a fraction of a second, culminating in a blast of immense power. This is the technology that ended the Second World War and introduced the world to the nuclear age. The second and far more powerful type of weapon is the hydrogen bomb, also known as a thermonuclear bomb. This device uses the opposite process, nuclear fusion. Fusion is the same process that powers our sun and every other star in the universe. Instead of splitting heavy atoms, fusion forces extremely light atoms like isotopes of hydrogen to merge together under immense pressure and heat. When these light nuclei combine, they form a slightly heavier nucleus, but the total mass of the new nucleus is less than the sum of the original ones. That missing mass isn't really gone, it's been converted directly into a colossal amount of energy, as described by Einstein's famous equation, E equals mc squared. This process unleashes even more energy than fission, creating an explosion of truly stellar proportions. So we have two different keys to unlocking atomic power. Fission is like breaking a large, fragile object into many pieces, with energy released in the shatter. Fusion is like squeezing two smaller objects together so hard that they become one, releasing an even greater burst of energy in the process. The atomic bomb is a fission device. The hydrogen bomb is a multi-stage weapon that actually uses a fission bomb as a trigger to create the intense conditions needed for fusion to occur. This bomb within a bomb design makes the hydrogen bomb orders of magnitude more powerful, capable of destruction on a scale that is difficult for the human mind to fully comprehend. Understanding this fundamental difference is the first step toward grasping the awesome and terrifying nature of these cosmic forces we've brought to Earth. Let's dive deeper into the science, into the very heart of the atom. The process of nuclear fission begins with a specific kind of element, one with a very heavy and somewhat wobbly nucleus. The most famous of these are uranium-235, plutonium-239. The number tells you how many protons and neutrons are packed into the nucleus. These nuclei are barely holding themselves together. All it takes is a gentle nudge from a passing neutron to push them over the edge. When a free neutron strikes a uranium-235 nucleus, the nucleus absorbs it, becomes incredibly unstable, and violently splits apart into two smaller nuclei, barium, krypton. This split is not clean, it's a cataclysmic event that releases a huge amount of energy, mostly as heat and gamma radiation along with 2 or 3 new neutrons. This release of new neutrons is the key to a chain reaction. If you have enough fissile material packed together, what scientists call a critical mass, each fission event will trigger more than one new fission event. One atom splits, releasing neutrons that cause 2 more atoms to split. Those 2 cause 4 more to split, then 8, 16, 32 and so on. This cascade happens with breathtaking speed. Within a millionth of a second, countless trillions of atoms are splitting in a runaway chain reaction. The energy released is so immense and so rapid that it creates an explosive force equivalent to thousands of tons of conventional explosives like TNT. An atomic bomb is essentially a device designed to assemble a critical mass of fissile material instantaneously, initiating this unstoppable atomic domino effect. Now let's journey to the stars right here on Earth to understand nuclear fusion. Fusion is the polar opposite of fission. Instead of breaking heavy things apart, we're building things up. This process requires light elements, specifically isotopes of hydrogen called deuterium, tritium. Deuterium or heavy hydrogen has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. Under normal conditions, the positively charged nuclei of these atoms repel each other fiercely. To overcome this repulsion and force them to fuse, you need to recreate the conditions found in the core of a star, temperatures of millions of degrees Celsius and mind-boggling pressures. When you achieve this, the nuclei slam together and merge. When a deuterium nucleus and a tritium nucleus fuse, they form a new, heavier nucleus, helium, and a spare neutron is ejected. Just as with fission, the products of this reaction have slightly less mass than the starting ingredients. This lost mass is converted into a pure, raw, and spectacular amount of energy, far more per atom than in a fission reaction. This is the engine of the cosmos. Every ray of sunlight that warms your face is a product of fusion reactions happening 93 million miles away in the core of our sun. A hydrogen bomb is a machine built to replicate this stellar process, even if only for an instant, creating a miniature star on the surface of our planet with devastating consequences. An atomic bomb, or fission bomb, is a marvel of brutal engineering designed to solve one problem: how to slam 2 pieces of subcritical fissile material together to form a critical mass at the precise moment of detonation. The little boy bomb dropped on Hiroshima used a gun-type design. It was essentially a cannon. A small, bullet-like mass of uranium-235 was fired down a barrel into a larger, hollowed-out target mass of the same material. When they collided, they instantly formed a supercritical mass. A neutron initiator then flooded the assembly with neutrons, kicking off the runaway chain reaction. The whole process, from the firing of the conventional explosive to the nuclear detonation, took less than 1,000th of a second, a testament to the speed of subatomic physics. Another design for a fission bomb is the implosion-type method, which was used in the Fat Man bomb tested at Trinity and dropped on Nagasaki. This design is more sophisticated and efficient. It involves a spherical core of plutonium that is subcritical and therefore stable. This sphere is surrounded by a carefully shaped arrangement of conventional high explosives known as explosive lenses. When these explosives are detonated with perfect synchronization, they create a powerful uniform shockwave that travels inward, crushing the plutonium core. This compression or implosion squeezes the plutonium atoms so close together that the core becomes supercritical, triggering the fission chain reaction. This method allows for a more complete and powerful detonation using less fissile material. Now let's scale up to the hydrogen bomb. A thermonuclear weapon is vastly more complex because it's a 2-stage device. The first stage is, in fact, an entire fission bomb. Its purpose isn't just to create a blast, but to serve as a trigger for the second, much larger stage. When this primary fission bomb detonates, it bathes the secondary stage in an intense flood of X-rays and creates immense heat and pressure. This radiation is the key. The secondary stage contains the fusion fuel, typically a solid compound called lithium deuteride, along with a central plutonium spark plug. The energy from the primary fission explosion is used to compress and heat the fusion fuel to stellar temperatures. This process, known as radiation implosion or the Teller-Ulam design, is what makes the hydrogen bomb possible. The X-rays from the primary fission bomb heat up the inside of the weapon's casing, creating a superheated plasma that pushes inward, compressing the secondary fusion fuel cylinder with unimaginable force. At the same time, the plutonium spark plug in the center of the fusion fuel is also compressed and goes critical, starting its own fission reaction. This adds even more heat and neutrons. This combination of extreme temperature and pressure from both the primary explosion and the spark plug is finally enough to initiate the fusion of deuterium and tritium atoms in the lithium deuteride, releasing a cataclysmic torrent of energy that dwarfs the initial fission explosion. It's a chain reaction of chain reactions. The story of the atomic bomb begins in the shadow of World War II, born from the fear that Nazi Germany might develop one first. This led to the creation of the Manhattan Project in the United States. Scientists, engineers, military personnel, led by physicist J. Robert Oppenheimer, the project worked in secret to turn theoretical physics into a functional weapon. The culmination of their efforts occurred on July 16, 1945, in the desert of New Mexico. The Trinity test, the world's first nuclear detonation, it involved an implosion-type plutonium bomb. Its explosive yield was about 21 kilotons, roughly 21,000 tons of TNT, creating a terrifyingly beautiful and ominous mushroom cloud that rose miles into the sky. This newfound power was used in warfare less than a month later. On August 6, 1945, a B-29 bomber named the Enola Gay dropped the Little Boy uranium bomb on the Japanese city of Hiroshima. The explosion was devastating, wiping out the city center and ultimately killing an estimated 140,000 people from the initial blast, intense heat, and subsequent radiation poisoning. 3 days later, on August 9, 1945, a second bomb, the plutonium-based Fat Man, was dropped on Nagasaki, resulting in another 74,000 deaths. These two events forced Japan's surrender, ending the war, but they also ushered in the atomic age and a new era of global anxiety, defined by weapons capable of annihilating entire cities in an instant. The end of the war did not end the development of nuclear weapons. It began an arms race. The Soviet Union, feeling threatened by the American monopoly, accelerated its own program and successfully tested its first fission bomb in 1949. This parody set the stage for the next terrifying leap: the hydrogen bomb. On November 1, 1952, the US detonated Ivy Mike on an atoll in the Pacific Ocean. This was the world's first true hydrogen bomb. The resulting explosion had a yield of 10.4 megatons, nearly 500 times more powerful than the Nagasaki bomb. The pinnacle of this madness was the Soviet Union's Tsar Bomba test in 1961. This monster of a bomb detonated with a yield of over 50 megatons, making it the most powerful explosive device ever created by humanity. Its shockwave circled the Earth 3 times. The sheer destructive potential of these weapons had grown from city killers to potential civilization enders, creating a precarious balance of terror that would define global politics for decades to come. The effects of a nuclear detonation can be understood as a devastating trio of destructive forces: the blast wave, the thermal pulse, the nuclear radiation. The first and most immediate effect is the blast. In the instant of detonation, rapid expansion of superheated air creates a shockwave of immense pressure that travels outward at supersonic speeds. This wall of compressed air is responsible for the physical destruction seen in photos of Hiroshima. Buildings flattened, structures pulverized, landscapes scoured clean. The second effect, arriving at the speed of light, is the thermal pulse. A significant portion of the bomb's energy is released as intense light and heat, creating a fireball hotter than the surface of the sun. This pulse of thermal radiation can last for several seconds and is capable of causing severe third-degree burns to exposed skin many miles away. It can instantly ignite flammable materials like wood, paper, fabric over a vast area, leading to massive firestorms that can engulf an entire city. In Hiroshima, the heat was so intense that it left permanent shadows on walls and pavement where people or objects had blocked the thermal rays, a haunting testament to the instantaneous and lethal power of the heat flash. The third and most insidious effect is the nuclear radiation. This is released in 2 forms: initial radiation and residual radiation. The initial radiation is intensely penetrating and highly lethal to anyone close to the detonation who might have somehow survived the blast and heat. It damages the cells of the body, particularly the bone marrow digestive tract, leading to a condition known as acute radiation sickness, which can be fatal within hours, days, weeks, depending on the dose received. This invisible killer adds a unique and terrifying dimension to nuclear weapons that conventional explosives lack. Residual radiation, commonly known as fallout, is the long-term danger. A nuclear explosion, especially a ground burst, sucks up tons of dirt and debris into the mushroom cloud, irradiating it. This radioactive material is then carried by the wind, falls back to Earth over hours, days, or even weeks, contaminating vast areas of land, water, and air far from the initial blast site. This fallout continues to emit radiation, posing a long-term health risk to anyone in the affected area. It can cause cancers, genetic mutations, and other chronic illnesses for years and even decades after the explosion. Fallout is what makes a nuclear war not just a series of explosions, but a potentially planet-altering event with consequences that linger for generations. Why is it so important for us to understand these weapons? Because in a democracy, ignorance is not a bliss. It is a peril. These are not abstract concepts from a physics textbook. They are real devices, thousands of them still existing today, many on high alert. They represent a unique existential threat to our civilization. Understanding the basic science of fission and fusion, the history of their development, the horrifying consequences of their use is not about fear-mongering. It is about responsible citizenship on a planetary scale. Ultimately, we are a species that has unlocked the power of the stars before we have fully mastered our own tribal instincts. By understanding this story, we arm ourselves with the most powerful tool of all knowledge. It is this knowledge that allows us to look up at the cosmos, not with fear of what we might do to ourselves, but with hope for the future we can build together if we choose wisdom over weapons.